Welcome everyone to Morro Coast Audubon Society's February community program on the sounds in the ocean, from ventriloquist lobsters to dancing crabs. And I don't know how many of you have been below the surface of the ocean waters as either a free diver, a scuba diver, or even a snorkeler, but the sounds under the surface are amazing. I'm going to kind of aged myself here, but it reminds me a bit of the old commercials for Sugar Smacks. I think it was Sugar Smacks, with all the snapping, crackling, and popping. I think those were the three guys: snap, crackle, and pop. Anyway, that's what it reminds me of sometimes when I'm down there. It's really, it can be quite loud. Just as a side note, tonight's program will be recorded and available on our MCAS YouTube channel. And if you have questions, you can write them in the chat and we'll get the responses to you, at least as many as we can, at the end of the presentation. So before I introduce the speaker, we have a couple of announcements. And so I'm Nancy Foley and I'm the president, but we welcome everyone on behalf of, I welcome everyone on behalf of the board. We have a very active board. We do a lot of things in our community, and I'm really proud of all the work that we do. So I'll start by saying that our fundraising focus this year will be Sweet Springs Nature Preserve, which we own. And if you enjoy this property or value what we're trying to do there with both conservation and education, please consider donating. There's a lot of work that we need to do there, including the boardwalk repair, some trail marking, work on the bridge, as well as some of our unplanned costs like eucalyptus trees falling, the fence building, and all of that costs a lot of money. So if your required minimum distribution is coming up and you need some place to put it, as a donation, please consider Morro Coast Audubon Society. So now I'll send it over to Robbie. Robbie, if you could tell us a little bit about the field trips coming up.
Hi, everybody. Welcome to I think this is our first community program, and we have just restarted the field trips after the month of January, when we did so much with our bird festival. It's the Rebel team here, and this is our first report of the year. So since Bob loves data so much, here's some from our 2025 field trip year. We had exactly 66 trips and 1,044 attendees over the year, and 727 people were on wait list, but most of those got into the pool for the 1,044 attendees. So that's a lot of people going out in the Morro Bay area, as well as all over San Luis Obispo County. As we begin our new year, we posted 4 trips in February. So please be patient as we get through this wet month. These trips may be rescheduled or canceled. We'll take advantage of our winter migrants that are still here by visiting Santa Margarita by pontoon boat, and Morro Bay shorebirds this month. And the following trips will be offered in March. We'll be visiting El Charro, Villa Creek for snowy plovers, a Sweet Springs habitat adventure, and a cruise on the bay. We're also conducting a walk in Sweet Springs for our National Estuary program friends during their State of the Bay in March. So hopefully I will see your name signed up on some of these field trips.
Yeah, thanks, Robbie. And I noticed there was a little bit of inconsistency between Robbie's mouth moving and the audio. So just know that we had some complications, and Robbie and Bob are both in the same room. And so I think there might have been a delay just because they're using 2 different computers in the same room. So I hope the rest of the program will go off without a hitch. So now, for a short introduction to our speaker, and I say short because if I actually gave her all of the accolades it would take up most of the hour. So I'll just go with the short introduction to Marie and our fellow board member, Dr. Marie Goeritz. Marie is a neurobiologist and educator who works to explore how animals sense and interact with their environments. She earned her Ph.D. in zoology and has conducted research at the Universities of Cologne, Cornell University, Brandeis, and the University of Auckland. Marie currently teaches biology at Cuesta College and serves on the MCAS board as the lands chair. She'd also like a lot of donations for Sprite Springs. And I really don't think she has free time, but I think she remembers that at one time she did have some free time where she enjoyed music, camera trapping, wildlife photography, and being on or near the water. I think that we at MCAS and our community are really lucky to have you, Marie. So take it away.
Thank you so much. That's a very, very generous introduction, and I'm really, really honored and pleased to be here. I am very excited because I care about Audubon so much, about Morro Coast Audubon, and I love talking about my research, and having those two things combined is like a really, really happy place for me. Before I start, let me start screen sharing, and here we go. So this talk is a little bit of a hodgepodge of research that I've done over the years, as late as 2019, I think, is the last data that I'm showing you. This is mostly done in New Zealand. Some of it, some background happened already during my time in Boston at Brandeis University, but just a teeny bit about myself or how I ended up doing this, because this is really my specialty. Or I started as a neurophysiologist working with these guys here, stick insects, and I studied walking and stick insects, trying to understand how one leg talks to the other leg, and that was really great fun. I did that in Cologne. And then for my PhD, I switched to these guys, crabs and lobsters, and started to study how the nervous system controls stomach movements. A lot of people don't know this, but the stomach system of crabs and lobsters is actually a model system that allows us to understand small networks, small neural networks for repetitive movement. Like when you walk, you don't think left foot, right foot, left foot, right foot. You have a central pattern generator that does that for you. Similarly, the stomach of the crab or the lobster has teeth inside. That's not similar to us, but it has teeth inside, and in a very similar manner, it moves very rhythmically, and that rhythmic movement is coordinated by a part of the nervous system that's called the stomatogastric nervous system. It's this little guy here. This is a part of the nervous system that I overlaid on the crab of Cancer borealis, on the carapace of Cancer borealis. And if you were to stick electrodes into this little tiny dot here, the stomatogastric ganglion, you would be able to record something that looks like this, which is alternating movement, alternating firing between different neurons. Excuse me. I was very, very happy with this, did a little bit of neuroanatomy, looked at where synapses are, but I really missed the field component, and I wanted to connect behavior, neuroanatomy with behavior, and I wanted to do this in a critter that I could study in the field. So I ended up in Craig Radford's lab in New Zealand. And this is where I got to do some field work. You see a little boat here. This is our lobster boat that we actually hired to go out and tag lobsters. Here's a tagged lobster. We were interested in lobster migration. Do marine preserves large enough? Do they move enough in and out of the preserve? Do the fishermen catch lobsters at the edge of the preserve, which they do? And so that was a lot of fun too. Craig's main focus is on fish hearing, and he was interested, and he got me to his lab because he was interested in crustacean hearing, and we thought that maybe we could stick some electrodes into crustaceans and see how, if we can record from nerves that might carry information from acoustic stimuli. I'll show you a few more of these pictures later on in the talk. This is a micro CT scan, which is one of the techniques that we used in Craig's lab to identify structures that might be involved in hearing, and the little stars mark the statuses, which are small agglomerates of or grains of sand that are glued together, that the crab or the lobster actually has to put actively into these little pouches. And they are mostly a gravitational organ, but they can be used to detect sound to some degree. In the process of this, I ended up sticking a hydrophone into a tank of a crab that we thought was actually mute. We didn't think that they could produce sounds. And I was able to record sounds from them. And that started a whole branch of, let's see who else can make sounds. And this is what I'll be talking about today, at least part of it. I'll also give you a little bit of a background of who else talks in the ocean. So quick outline, we'll talk about soundscapes in the ocean. What are the sources of sounds? What examples are there for sound-producing organisms? There are so many, and I cannot possibly show you all of them. A lot of them are very bizarre, very cool. So I just picked a few select ones that I want to play to you so you can get a feeling for what's out there that is not whales and dolphins. We'll talk about reef soundscapes, which is something that I did not know about until I went to New Zealand. Each reef has a fingerprint soundscape or sound signature, and that is used by a lot of animals to find the reef. It helps them actually settle. So we'll talk a little bit about that, and then I will talk about my research on paddle crabs that I did with a wonderful graduate student, Ashley Flood. So these are sounds that we recorded, behavioral context for these sounds. What does it mean? What can they hear? And this is, we'll see if we get that far, or how far we get into that, especially in the what can they hear part. But this is my plan for today. So let's talk about soundscapes. Sound is the ocean is really loud. As Nancy already said, if you're a scuba diver or a snorkeler, you will notice that it's not this tranquil environment. You hear lots of popping, crackling, weird rasping, all sorts of sounds. And one of the reasons for that is that water is denser than air, so sound moves a lot faster. It moves about 4 to 5 times faster underwater than in the air. So that means roughly about 1,500 meters per second. This also means that sound reaches very far on its own because water is so dense. But then in addition to that, sound also gets reflected by different layers. So depending on the pressure and depending on the temperature of different layers in the ocean, sound waves can actually be reflected upward or downward. And you end up with these channels in the deep ocean where sound can travel hundreds to thousands of miles. And this is something that whales and large marine mammals use to communicate over huge distances. The type of sounds I will be talking about today is more here in this little corner. Here we have a little crustacean, a little lobster. So this is a relatively short distance sound. It's still farther than you might think, but one of the interesting things, if you're a physicist and if you're a marine biologist, you kind of have to think about it at least a little bit, is that sound under the water consists of 2 different components. One is called the particle motion component, and one is called the pressure wave component. I don't want to go too far into it. I'm just going to show you what that means. So if you have a speaker here and you have just sound waves, you actually have a wave that propagates away from the speaker, and within that wave you have oscillation, sound pressure oscillations that create particle perturbances or disturbances. So we think that for crabs and lobsters and small and animals in the reef, the particle component is, so this vibration component is really important. In order to detect the wave component, you actually have to have an air-filled cavity. So fish have a swim bladder that could function like that. Crabs, lobsters, most invertebrates don't have air-filled cavities. So just from a physics point of view, it's probably not possible for them to detect frequencies above 2 kilohertz unless we find an air-filled cavity, which I still hope to find one day, but so far it doesn't look like it. So the dominant component is the particle motion of the sound wave, and that's something that's that many invertebrates definitely can detect. So where does the sound come from? A lot of it is natural sounds, wave motions. Again, if you've been snorkeling, you know this. Waves break, they make sounds. The weather makes sounds. Wind creates a lot of sound. There's actually sounds from seismic activity that can travel very, very far in the ocean. And then a lot of sound comes from animal behavior and animal communication. In addition to that, we have human-generated noise or anthropogenic noise, and that is becoming more and more of a problem. It has increased dramatically over the last 10, 20 years. About 90% of the human-made noise comes from ships traveling. And again, because sound reaches so far, a ship that's pretty far out off the coast of Morro Bay will still a lot of animals will be able to hear that in our estuaries, or at least in the entrance of the Morro harbor. There's a lot of industry that contributes sound, constructions, wind farms, especially the building of wind farms. Once you have a wind farm, the biggest noise or the largest generated noise probably comes from vibration of the gearboxes. But building these wind farms can definitely add a lot of noise. This is all very interesting, and I think also very important to worry about, because some animals are very, very sensitive and will receive irreversible damage if they're exposed to anthropogenic noise. But for the sake of this talk, I'm going to focus on animal behavior and animal communication and sounds that are related to that. There's many, many species in the ocean. There's over hundreds of thousands of species. You might wonder how many of those actually make sounds. And this is a recent review, a literature review, which is really just a very brute force review that looked at about 33,000 species that have been studied. There's many more that have not been studied. And of those 33,000 different species, about 700 produce active or passive sound. So active sound means it's a sound that the animal generates with a purpose. Passive sound would be sound that is just a side effect of the animal's behavior, like an animal walking around, moving rocks that generates a sound, but that's a passive sound, or at least for the purpose of this study. In addition to that, just based on where these animals are in taxonomy, there's probably another 21,000 that are very likely to produce sound. And all these species include marine mammals. So if you think about sound in the ocean, you probably first think about the song of whales, about dolphins, about other marine tetrapods, and they are definitely included in this. But many, many fishes produce sounds, many more fishes than I realized until I started looking into this. And many invertebrates. So my specialty is invertebrates. I'm an invertebrate neurobiologist, so this is what I love and breathe. But I'll show you a few examples of fishes just because they are so bizarre and so interesting. Why would animals use sound? It's a little bit of a no-brainer question, but still kind of fun to ponder. The ones that immediately come to mind is communication. Most animals communicate within a species or between species. Predator avoidance, if you can hear a predator coming, you can avoid it. Prey detection, if you can hear your prey, you can move towards it. Navigation, I'll show you an example for that when we talk about reefs. So overall, sound is a really, really great channel because it's not very perturbed by or not disturbed by weather events. The water can be as murky as you want. You will still be able to hear. It's a very consistent sensory channel. So it makes a lot of sense, evolutionary speaking, that animals would use this channel a lot. So let's talk about reef sounds. I mentioned it earlier, each reef has a unique soundscape. So it's almost like an acoustic fingerprint. So but just by listening to the sound of a reef, you can tell it apart from a different reef. And if you are an expert on this, you will be you can listen to different recordings of reefs and will be able to make at least predictions of what kind of animals there are, where this reef might be located. Animals are a lot better at this than we are. So there's a lot of evidence that crustacean larvae, which disperse, the eggs disperse in the deep water, and these larvae have to come back to the reefs eventually. And it turns out that sound cues might be one of the ways for these larvae to identify home reefs. So Jenny Stanley has done some really beautiful research together with Craig Redford about crustacean larvae, and found that if you play back the sound of, if you give crustacean larvae an option to move either away to a sound source that is different from their home reef, or towards the sound source that plays or replays sounds from the home reef, they're more likely to move towards the home reef. They also seem to grow faster if you expose them to sounds of their home reefs. And there's a lot of evidence that they settle faster if you play them the sounds of the home reefs. So the other thing that's pretty cool about reef sounds is you just listening to a reef, you can tell how healthy or how unhealthy it is. And this is something that not only humans can tell, but many organisms seem to be able to tell the healthiness of a reef just based on a structure. So this is there have been a few experiments about this. I'll show you one actually on the next slide. Before I get there, I just quickly want to summarize what you find on the reef, or what's contributing to these sounds. I already mentioned waves, weather, natural features of the reef. So the shape of the reef will have a very large influence on what the reef sounds like. But what invertebrates live on the reef? And the biggest component of that is probably snapping shrimp. So when you go scuba diving, you hear all these clack, 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 clack sounds, these popping sounds. Most of those will be snapping shrimp. Make very, very loud sounds. They're in the range about 2 kilohertz or above 2 kilohertz. They produce them by, I say snapping their claws here, which is not quite true. They do snap their claws, but it's not the snapping that actually makes the sound. It's a physical phenomenon that's called a cavitation bubble, and I'll show you what that means in a moment. In addition to that, we have a lot of fish that produce a variety of sounds, grunts, pulses, songs. A lot of times those songs are associated with mating, with nest keeping, reproduction, but also with feeding behavior, typically in the range of several hundred hertz. So this is an example of what a healthy reef sounds like. And this is from a recent study from 2024 that looked at how likely are coral larvae to settle on a reef depending on the sound. I'll just play this. So hopefully you hear there's a lot of popping, snapping. This is a healthy reef. On the other hand, a degraded reef is very quiet. It doesn't matter what caused the degradation, if it was a biological event, a predator that ate all the corals, if it was a reef that was over-visited by scuba divers, especially scuba divers who are inexperienced and break off or destroy a lot of the reef structure with their fins when they kind of bounce into the reef. It could be pollution. Either way, these reefs are very, very quiet. And I have an example here of what that sounds like. So you still hear a little bit of crackling, but it's nothing compared to the earlier one. What these people tried, so this is research out of Woods Hole and by the Mooney Lab. They had they took a few test sites and replayed the sounds of healthy reefs at a degraded reef, and it turns out that coral larvae actually settle preferably or at higher rates at reefs that play the healthy, happy sounds. So this is a really promising technique to recover reefs, or to help reef recovery, in addition to removing whatever destroyed the reef in the first place, playing sounds of a healthy reef might speed up recruitment of coral larvae, recruitment of the reef by coral larvae. Lamont et al. 2021 is one of the earlier studies that looked at this too. I mentioned that I'm going to show you a few examples of cool animals that make sounds. So this is the story, just example section of the talk, and there's really not much story to these examples except that I'm going to point out why I think these are cool or interesting. But we do have a lot of soniferous fish. Like I said, I'm only going to have time to show you a few. One of them that you find at many reefs are the damselfish. This is a very aggressive fish that uses sound as part of a territorial and courtship behavior. Damselfish produce their sound by snapping the pharyngeal teeth and resonating it against the swim bladder. So it's a pretty complicated system that uses this makes a sound with the teeth and then uses an amplification through this swim bladder. And it sounds like this. It's almost like a cat purring. It's a very soft purr. I have maybe a little bit better example on the next slide here. So this is a surgeon major fish that produces sounds by the same mechanisms. It's a type of damselfish. So lots of chirping, lots of clicking. And again, you hear the clicking of the snapping shrimp in the background. One of my favorite fish is the plainfin midshipman fish, which is a mouthful to say. This is a beautiful fish, or I think it's beautiful, that lives in, that has nests that are tended or created by the male. This is a large male, it's called a type 1 male. They make very, very monotonous, kind of soothing sounds. This is a female that was attracted by the songs of the male. And then this one here is another type of male. It's called a type 2 male or sneaker male, which will come in and go unnoticed by the big male and fertilize probably up to 50% of the eggs that the female laid. So the big male will keep those eggs and take care of the eggs. This little sneaker male comes in. This fish is a model system for understanding how hormones and how neural networks control acoustic communication. So at Cornell, there's a lab called the BASS lab that has studied these fish for many, many years and uses them as a model system. So the amount of sex hormones that you find in these fish is very different for these three types. The types of sounds that are produced, the more complex sounds are produced by the big male in order to attract a female. These little guys do produce sounds, but they are mostly as a form of aggression or antagonist behavior. Like if you confront them, if you corner them, they will produce sounds, but they will not produce sounds to attract a female. This is what they sound like. Basically like a foghorn. And in the 1970s, I believe, there was a huge mystery in San Francisco. People were complaining about this awful, awful sound that kept happening at night. And nobody could figure out where it was coming from. There was all sorts of investigations launched trying to figure out who was humming and producing these ongoing sounds until a scientist actually joined the riddle and listened to the sound and realized this is midshipmen that are humming at dusk or at night and are producing the sound. If you think this is a soothing sound, you can actually go to Nature of Things, which is a YouTube channel that provides you with 12 hours of plainfin midshipman humming. A very either annoying if you want to sleep right next to it, or soothing if you use it as a meditation type of sound. Another very cool fish you might find at different reefs is the black drum. I'm playing this example to show you that it's not just monotonous sounds. It can be very diverse and almost like, to me, a lot of the sounds that you hear in the ocean are very similar to going birding and listening to the dawn and dusk chorus of birds. There's so many different ways to make sounds, very simple or very complicated ones, and the reasons to make those sounds are very similar too. So this is a black drum. If you go fishing, you might actually have heard that sound if you catch a black drum. Let's move away from the fishes, though, towards to the invertebrates. Again, I'm just showing you a selection. There's many, many more, and it's one of those fields that when I started working on those in 2015, the idea that marine invertebrates produce sound was kind of poo-pooed a little bit. There were a few examples where it was clear, yes, this crab has stridulation grooves on its callipede, so that we think that it makes sound. We knew about one or two examples. We knew about Californian lobsters. If you capture Californian lobster, spiny lobster, Paniliurus interruptus, you will know that they have antenna plates and they make a very kind of aggressive or angry sounding sound from rubbing the antennal plates. But overall, invertebrates were not considered to contribute much to making sound in the ocean. And this has changed over the last few years quite a lot. The main mechanisms by which crustaceans make sounds are stridulation, cavitation, and muscle contraction. What that means is stridulation, you have a structure on one appendix that moves across another structure with what's called a stick and slip mechanism and produces kind of a sound pulse. So spiny lobsters, I just mentioned those, Paniliurus interruptus. When they rub these antennal plates, they build up pressure. It's the antennal plate sticks, and then eventually it slides or slips and makes a very loud sound. There's a lot of different forms of stridulation, so you can have like a plectrum rubbing against a series of ridges to make more rich sounds. The other one is cavitation, and this is a very, very bizarre form of sound generation. Like I mentioned, snapping shrimps don't actually make the sound by just snapping their claws. They make the sound by creating a bubble of very low pressure that collapses on itself, becomes incredibly hot, like 5,000 Kelvin hot. It's like surface of the sun level hot. Of course, it's in a very, very small volume, so it doesn't actually cause a lot of damage on a larger scale, but that sound, and I'll show you an example or a little video of that in a moment. So that bursting of that cavitation bubble causes a sound. And the third type of sound that we find in invertebrates is muscle contraction. So this is a lot of times a type of grumbling sounds that, for example, mantis shrimp make, where you have a vibration of muscles against the carapace, and that causes this rumbly sound. Again, I'll have an example of that in a moment. So snapping shrimp, these guys that contribute so much to the sounds that you hear when you go scuba diving or snorkeling in a reef. You can hear it again. If you look at the structure, you can see this massive, massive claw, and that's really important for creating the sound. And I can show you what this looks like in slow motion. So as this claw closes, it has a little channel in it, and through that channel it produces a very, very fast water jet that gets expelled, and it comes out so fast that it causes what's called a cavitation bubble that then very, very violently collapses. And this has three effects. One of them, like I said, it creates incredible heat and actually a light flash that you can see. So it's it creates photons that if in the dark you will see that as a very short light flash. It stuns their prey, so the shock wave of this cavitation bubble collapsing stuns their prey and helps them catch the prey. And it also produces a very loud sound, about 210 decibels. So it's very, very loud. And the sound is used for hunting, and we also think for communication. So this is what it looks like. I'll play this video a few times so you can focus on this cavitation bubble forming here. Let's see it again in a second. This is so this is very, very short flash, which is over in a split second. If the claw, the snapper claw moves very, very quickly. This is data from the Verlui lab from 2002. And if you look at these individual frames, you can see, so this is the claw open, and as it closes, right after closing, you can see this cavitation bubble forming here. And here's still an intact bubble, and now it collapses onto itself, and this collapsing is actually what causes the sound. So if you line up the timing of the bubble collapsing with the sound, you can tell the sound does not come from the snapping of the claw, it really comes from the collapsing of the bubble. And then a little bit more detail, you can see here, this is the cavitation bubble, and here it collapses. So this is, we thought this was a very unique example of producing sound. It turns out that there's quite a few animals that do this. And, oops, where am I here? Another example would be the this invertebrate worm. It's called Goeritz kimurarorum, which also produces a sound that is, so far we don't actually know how it makes the sound, but just the signature of the sound is in frequency, in timing, is very, very similar to this cavitation bubble of snapping shrimp. So we think that might be the same thing. They're very cute worms. Let me go back one slide before I forget this. Just a sidebar, since we just talked about snapping shrimp, you might ask yourself, how do they hear? And I mentioned the statocysts earlier. So this is a CT scan, a micro CT scan I did of a snapping shrimp. I basically took the snapping shrimp and put it into a very, very high power, but very, very small CT scanner that the University of Auckland had. And scanning through this, through the snapping shrimp, and this is a dead snapping shrimp, of course, you can see this, these grains of sand, this conglomerate of sand that is kind of glued together with this viscous material. Every time the shrimp sheds, it has to get rid. It gets rid of the statocyst. It has to find a new statocyst. It has to find new pieces of grain that it puts into this little pouch, and then they get glued back together. And this statocyst sits in an area that is covered with sensory hairs. So if a sound wave comes, it moves the animal at a different speed than it moves this little ball of sand grains, because this is very dense. And movement of the sensory hairs around the statocyst is how the shrimp or the crab or the lobster can detect low frequency sounds. So this doesn't work for high frequencies, but for low frequencies, this is a very good way of detecting vibrations and low frequency sounds. Oh, this is the wrong direction. Okay. Here's another very loud animal, which is a mantis shrimp. This is a tropical one, but we also have a California version of it. And I want to show you how the mantis shrimp makes sounds. This is an example of sound that is, well, there's multiple ways how mantis shrimp make sound. They do the rumbling sound that I mentioned earlier, and I'll show that to you. But they also make passive sound by the way they hunt. They can, they have this little club-like appendage that can be used to knock onto shells in yeah, I have a video on the next slide that shows you how it actually breaks open a shell. The force of this, the speed and the force with which this appendix accelerates and knocks against the shell is of a mussel is so fast and so strong that it can actually break the glass of an aquarium. So if you have mantis shrimp in a tank, you have to be very careful about how thin or thick your glass is, because it might break the wall of the aquarium. In addition to this, these are also super, super cool animals because they have the most complicated visual system that I can think of, at least a number of photoreceptors. We have 4 photoreceptors. These guys have at least 12, possibly even more, which means that even to us, they are already very, very colorful, but we only use our 4 photoreceptors. You can only imagine how colorful they will be to each other. Here's this video of a mantis shrimp breaking open a little mussel. You can see it's already it already punctured a hole in there. It keeps going a few more times until it can easily access the inside of the mussel, or clam actually. And my apologies, I'm a neuroscientist, so a lot of times when I say clams and I mean mussels and the other way around, I know that for a marine biologist that's, oops, that can be a little bit annoying. I hope you stay with me though with the when we talk about the underlying neural networks that control this behavior. So the California mantis shrimp is known to produce this rumbling sound that I mentioned earlier. So this is done by vibrating its carapace, which is its outside shell. Again, very low frequencies, about 167 hertz. These rumbles last about 200 milliseconds. And if you, I mentioned the dusk and dawn chorus in the ocean, if you go snorkeling towards the end of the day or very early in the morning, you will notice that the reefs are much louder, much more active. There's more foraging happening, there's more mating behaviors or courtship happening. And so these guys significantly contribute to this dusk-dawn chorus. They're very active when they're feeding or when they're guarding their burrows. This is what it sounds like. Very, very low rumbling sound. Other invertebrates definitely are able to produce sounds as well. We know that bivalves can produce clicking sounds. There's a coughing sound of scallops that has been described. Cephalopods, I don't know any example of them producing sounds other than using their siphon. So they can eject water through their siphon, make hissing sounds, popping sounds that way. They are, however, very, very sensitive to sounds. And if we have time to talk about human-generated noise, these are one of the groups that is probably the most damaged by human sounds, aside from mammals, marine mammals. They are their status is very extremely sensitive to loud levels of sound. Snails, lots of snails make sound passively because they have this organ called a radula that is like a rasping organ that allows them to just like sandpaper to remove algae from rocks. And that definitely makes a loud sound. You can record that with a hydrophone. There's some evidence that snails move towards other snails just based on their sounds. So we do think that snails actually might have more sophisticated sound, or at least sound interpretation systems than we first thought. Many more. The one that I want to show you now is the one that I actually worked on myself in New Zealand. So this is the New Zealand paddle crab. Ovolepis, let's see here. There's multiple species of Ovolepis, and all of them are known or are presumed to be able to produce sounds, because if you look at their claws, you can see at the underside of the claws these ridges that are very typical for animals that produce sounds through a stridulation mechanism. It's very similar to what you find on crickets, for example. However, this was just based on anatomical observations. There hadn't been any experiments that really showed what kind of sounds these animals can produce. So when I joined Craig's lab, we put a hydrophone into a tank with Ovolepis. Oops, where am I? Yeah. Ovolepis catharus, so New Zealand paddle crabs, and lo and behold, they produce a ton of sounds. However, we didn't actually see them doing any stridulation. So this was a big mystery, because we, up to that point, the idea was that the sound that people had heard with or associated with Ovolepis were actually produced by the stridulation. And we, when we had this master's student, Ashley Flood, in our lab, who is a very, very talented student, very driven, this became her master's thesis, trying to figure out what kind of sounds do Ovolepis actually produce? Is it more than one? And in what context do they produce them? So we caught a lot of Ovolepis, or we collected them in the estuaries, in the mudflats. This is around Goat Island in the North Island of New Zealand. They are subtidal species, so they live around 2 meters to 100 meters. So they're very easy to catch if you just put out some bait and some traps. Very abundant open sandy beaches. The males are much larger, about 15 centimeters across. The females only about 10 centimeters, a little bit more than 10 centimeters across. They're pretty aggressive. I worked with a lot of East Coast species, which are pretty mellow compared to these crabs. They, if you pick them up, you have to be very fast, otherwise they will definitely pinch you and possibly puncture your fingernail. The male can only mate with the female when the female shell is soft. So when it's mating season, the male will find a female, grab it, wait until it is mated, and walk around with the female for days until it can actually mate with the female. And this becomes important in a moment. So the questions were, what sounds do they produce? What are the behaviors we can see? What are the mechanisms that produce those sounds? This is what our setup looked like. We had a large tank, and in that tank we had our crabs. We only put them in for the experiment. We had holding tanks that were separate. We put a hydrophone in there. We had a CCTV camera mounted on top of that tank. We used red LED lights because the idea is that crabs cannot see in the red range. However, we do feel like there might actually be some sensitivity to red lights that we did not take into that we were not aware of before. We had a GoPro mounted on the bottom, so we could actually record the behavior more accurately. And then we put crabs in there, and we would just have them alone, we would have them together in groups, we would have them feeding, and then when we were lucky enough to get mating crabs, we would put the mating crabs in there and see if that caused any special sounds. And spoiler alert, it did. So the three types of sounds that we recorded from these animals were the rasp, the zip, and the bass sound. And here's the frequency spectrum of all three sounds. And I'll play them to you. So this, the rasp is the one that we first heard. That was the very first one. We put the hydrophone in there. And the zip sound it's kind of a rubbing sound, much more consistent with stridulation, and with this one we actually did see the animal move, but this is a very rare sound. We only saw that in mating animals. And then the bass sound, which I will play it, but unless you have an excellent speaker system, you're probably not going to hear it. It's a very subwoofer type of sound, very, very low frequency. It's more, you feel it more in your stomach than you can actually hear it. It's like on my computer, I barely hear it, so it really goes like whoa, whoa, like that type of sound. So let's look at the rasp sound first. Just a reminder, this is what it sounded like. Really very much like a cricket. That sound was produced by males, by females, and by juveniles. We noticed a lot more of those sounds when we were feeding the crabs, so we thought that there might be a connection to feeding. They seemed to be very excited when we were about to feed them, and that's when we also recorded a lot of the sounds. Like I said, the sound was previously recorded in other Ovolepis species, but falsely attributed to the stridulation movement of the chelipeds. At this point, we thought it's an unknown mechanism. We don't know this. We can't see anything moving from the outside of the crab. We noticed that it seems to be the length of the rasp seem to be longer in males than in females. Like I said, related to feeding, here have a timeline in minutes. So there was no food in the tank up to this point. This is where we added food, and then we found a lot of increase in these rasp sounds. And like I said, that we also had examples where as soon as we entered the room with food, especially if we had them for a while, we would start seeing a pickup of those rasp sounds. So yes, we think this sound is feeding related, about 31 times more likely than in non-feeding trials. We were wondering if the crabs use those rasps as a cue in order to find food. So Ashley had a control tank that these are 4 crabs that moved around, or mostly stayed stationary. And in this example, she played back rasp sounds from a speaker, and that increased movement behavior in at least 2 of the crabs. So this one here stayed stationary, this one stayed mostly stationary, but this crab here, this guy over here, and this crab over here started moving around when they listened to rasp playback sounds. To us, it looked as if they were looking for the food source. The zip sound is the one that we found especially in mating animals. And play it again. And this is a sound that we only found produced by males. And it was associated with very aggressive behavior towards a mating pair. So when we had a male holding a female, walking around with a female for hours and days, and we added another male to the mix, a lot of times the second male would walk towards the first male, stand in front of the male, sometimes in sort of a threatening posture, and produce that sound. The way it was produced was by rubbing the first walking leg against these ridges of the chelipeds that I showed you those ridges earlier. So it's really like a plectrum mechanism, very similar to crickets. Here you can see them again. So rubbing one of the first walking leg against these ridges produces this zip sound. Ashley made a little sketch of what this looks like. So here's the cheliped is moving back and forth. Here's the first walking leg with the ridges, and this is where the sound is produced, really at this intersection between the first walking leg and the cheliped. Then finally, the bass sound is the one that puzzled us the most, because it again was only related to mating, and when animals were producing the bass sound, they were again standing in front of the mating pair and performing what to us looked very much like a dance. It was a swaying back and forth on its legs without actually moving, without walking, just swaying in place and producing this bass sound. So we have no idea what the mechanism for the bass sound might be. And like I said, it's a very, very low frequency sound. So maybe it is similar to the California mantis shrimp, where you have muscle movement against the carapace that is causing it. But from the outside, just looking at the animal, it was not obvious what produced those sounds. You can see this is a pair where mating begins here around 8 p.m. Mating stops around 11 p.m. The male was still holding the female, And we added additional males to the tank. And as soon as we added the additional males, they started producing a lot of the zip sounds, some bass, some zips, and kind of lasted for a few hours before they would stop it. It looks very aggressive when you observe it. And I feel like this movie, I just tried this movie and I think it might not be playing. Yeah, no. But what you would see in this movie is the swaying behavior, the back and forth swaying of the crab. So this was really cool and exciting. The big puzzle was how does it produce the bass sound, and how are those cricket-like sounds, the rasps, produced, since the animal is not moving. Those were the ones that were related to feeding. And this is where my previous work came in this really bizarre coincidence. I mentioned earlier I worked on the somatogastric nervous system. So if you open up, this is a Jonah crab, which is a species that you found on the east coast of the US, or a New Zealand paddle crab, you will see teeth inside the stomach. There's one medial tooth and two lateral teeth, and you'll see those teeth have ridges. We always thought these ridges were just for chewing, and made a lot of sense that you have ridges in order to chew mussels, all sorts of little critters that you catch. And depending on what kind of food you feed the crabs, you can actually see different patterns in coordination of those teeth. So there's a lot of modulation happening in the system. The New Zealand paddle crab also has teeth. They look they're a little bit more fragile than the Jonah crab, which is not surprising because the crab is also a lot smaller and a lot more fragile. But we thought maybe the sounds are related. If you can't see the crab moving from the outside, maybe the sounds are related to the movement of the teeth. And this is where we started building robo-crabs. I'm showing you an example of a Jonah crab here. I did the same with the New Zealand crabs, though. So I would anesthetize a crab, implant electrodes, like very, very small silver wires in the vicinity of the two big stomach muscles. If you were to do if you do a nerve recording, or if you get it close enough to one of the nerves, in this case the LVN nerve, you can see the activation of pyloric muscles on this on this recording. If you go into a more stomach teeth area, you can see a similar pattern of activation of the stomach teeth. So these are chronically implanted. These you close up the crab. It has a lot of waterproofing material because these sites are very prone to leaking, and then you lose the signal. We have a little float that allowed us to connect with a little plug to an amplifier, and actually do a nerve recording of these nerves. Today you could, so this is experiments that I did 2015 to 2019. By now you can probably do exactly the same thing wireless with a lot less headaches, because we get a lot of corrosion in these wires. At the same time, we put a hydrophone in the tank, and what we were looking for is simultaneous activity of the sound, of the rasp sound, and activity on those muscles that move the stomach teeth. And this is what we found. This is a GM muscle. It is one of the big muscles that moves the lateral teeth. And every time the GM muscle moved, we recorded a sound on the hydrophone. And this is a different crab, the same thing, lots of activity on the GM muscle, perfectly lined up with sound activity. In the absence of feeding, we also had, so this is a crab that was, so because you could argue, well, if the crab chews, of course it makes a sound, of course it moves the muscles, but even in the absence of feeding, every now and then we would record those rasps. And this is an example where we had a rasp here and activity on the GM muscle, another rasps here and activity on the GM muscle. This is not as beautiful of a recording as before, but you can see that they correlate. And here's another one in the absence of feeding. It's probably a lot better correlated. So all these nerve recordings showed us that we really think they use the stomach teeth to produce a sound. So it was really, really exciting. It was not described at the time. By now, we found this in at least 2 other species, or other labs have found it in 2 other species. The reason this is really exciting to me personally, and this is going a little bit beyond the scope of this talk, is that this type of one of the things that is really puzzling about the stomatogastric nervous system is that it is hugely modulated. There is hundreds of different combinations of modulators that produce that you can put onto this network. Dopamine, serotonin, all sorts of peptides, and all of these different combinations of neurotransmitters produce a different rhythm, and that has been great in order to study this nervous system very well. As we learned a lot about the synapses, we learned a lot about ion channels that underlie this activity. But big question was always, why does a crab need to be able to modulate such a simple system in such a complicated way? And I think one of the answers could be that this system is not only used for digestion, but also used for communication. So you would expect to have different ways of activating these teeth if your purpose is communicating, as opposed to just chewing food. So this is something that I would love to continue, and I'm in the process of setting up a little tank at Cuesta College, because I think this is a beautiful, beautiful prep that can be very easily done with undergrads. So hopefully there will be some results in the next few years about whether or not any of the local species produce sound, and if they do, if this is also related to behaviors and communication. I want to finish with the physiological effects of anthropogenic sounds. This is just one last slide that I want to throw out here, because it's a very recent paper that looked at the effects of human-generated noise on different species. So in brown, you have invertebrates. It's not just squid, it's all sorts of invertebrates. One of the squids that is particularly sensitive to sound is the hummingbird. Oops, forgot it. I'm blanking on the name. I think hummingbird bandtail squid that has a status that gets very easily damaged by sound. This is a lot of fishes have there's a lot of studies that looked at the effect of sound on fishes. The colors here tell you if it's a significant, or the stripes tell you if it's a significant effect by sound or not much effect, and then the same for marine mammals. So in different types of sound, traffic sound, seismic sound, pile driving sound, sonar sound, industrial sounds, has been studied to different degrees on different species, and some of them have a lot of, for example, seismic sounds have a lot of effect on invertebrates. Pile driving also has a lot of effect on invertebrates. Sonar does not seem to bother invertebrates all that much. Traffic probably more effect on fishes than on invertebrates, but there's a lot to think about when we, as we put more and more things into the ocean, as we get rid of marine reserves. We really want to be careful about making sure that we have protected zones where animals actually can behave the way they usually behave without interruptions. I'm going to stop here. I would have loved to tell you a little bit more about rock lobsters also making sounds and about the organs that these animals use to recognize the sound, but I don't think I have time for this. So I just want to finish by thanking Craig Radford, who got me over to New Zealand and who really spearheaded this with his research on fish. And at the moment he studies shark and sound in shark. Hearing in shark. Ashley Flood, who was this phenomenal graduate student, she now has gotten her Ph.D. and she's really fantastic. Kevin Tai was a master's student that worked with me on hearing. So we did some recordings of the nerve near-statocysts in different species to see if animals actually respond to sound. And there's a whole story about how a lot of the sounds that we listened that these animals produce are higher frequency than what we think they can hear. And then Errol Murray, who was and Peter Brown were fantastic lab technicians, and Dane Gernicke at the University of Auckland, who was amazing to work with doing those micro CT scans. Any questions? Let me just stop sharing here so I can actually see you. Any questions? I'm happy to take some questions now. I think, oh yeah, I'm a little bit over time. But
I don't see any questions coming in the chat yet, but we'll give people a minute to type them away. And I, for one, can tell you my next experience scuba diving won't be the same. I'll be looking around to see who's snapping, cracking, and popping over there. Yeah. Yeah, it's really very interesting, and the fingerprint of each reef is something that I didn't know about either. Oh, very interesting.
I was really fascinated when I first learned about that, and also the idea that these, we know about many terrestrial arthropods that have very, very complicated social behaviors, and then we talk about lobsters as the bugs of the ocean, and there's a lot. I think there's a lot more to the way they interact than we think of when we put them in the pot.
Yeah. Can you see the one question just came up? Do you find more sounds at the lower or higher frequencies, and any advantage for one or the other?
So yes, so the sounds that we recorded in these crabs are they span a wide range of frequencies up to 6 kilohertz, and that's really I think that's consistent between these animals and other crustaceans. However, like I said, we think that they can only hear the particle component of sound. At least if they use the staticist, we know, or most staticist recordings have shown that they work really, really well for up to 2 kilohertz. So there's a discrepancy between the sounds that these animals produce and the sounds that we think they can hear. And I personally would love it if there was another channel that we don't know about yet. So it's not only the statuses, they also have like hairs that work in a similar way, on analogous way to the side organ in fish, sideline organ in fish, that are sensitive to sound and vibration, but again in the low frequency range. So anything below 2 kilohertz would make sense. Everything above 2 kilohertz does not make sense with what we know about right now. However, there might be more.
Mm-hmm.
Hey, Marie, this is Bob. I'm going to jump in and ask a quick question. I have hundreds of hours of GoPro scuba diving and snorkeling, and I have to admit, I had never turned the sound on before.
No.
So now I have to go back and watch them all again, and Robbie and I, and turn on the sound. But the question is, if I do, is there an app like Merlin that's going to tell me what I'm listening to?
Oh my goodness, that would be wonderful. Yeah, I don't think there is one, but I know that if you've been scuba diving south of here, and where there's like spiny lobsters and they sit together in these little caves, if you have any recordings of that, I would love to hear them, because I would expect them to make a lot of sound, a lot of type of sound. But yeah, I don't know. We should work on an app.
Well, these are mostly in Bonaire, so thank you.
Well, thanks for coming. Thanks for listening. Sorry for going over time.
Yeah, not a problem at all. It's a pretty soft 8 o'clock, but we really appreciate everything that you've explained to us, and many of us will never look at being under the water the same again. So thanks, and thanks everybody for joining. I think we had over 50 people, and I know that once we get it on the YouTube channel, it will get a lot more. And I see all kinds of hearts and hand clappings coming up the screen. So yeah, thanks so much, Marie. Really appreciate it.
Thank you for giving me the space to talk about this, because like I said, I get very excited, and I hope there's going to be more. I think it's a beautiful system to work with undergrads. So my hope is to actually set up a little tank at Cuesta, and then let's see what else makes sounds.
All right. Well, thank you. Thanks, everybody. Thanks, Marie. Thanks, Bob, Robbie, and we'll talk next time.